And then some people really were not very happy with this. Some of the reviewers changed it. It was equally correct. Okay, we could do the same thing over here, I suppose. But you could say, well, yeah, okay. So the CDF is, I guess, if you have our probability density function like this, then the CDF is going to be monotone, increasing, and it's going to start at 0, and then it's going to grow, and then at the right value, the support, this is called this part is called the support. It's sort of what's holding up the distribution, and the CDF always ends at 1, and the slope of the CDF at any point is going to be the density function, right? The slope is the density function. So wherever we have sharp increase, it's going to be here, and if it's flat over here, it's going to be linear, right? When it's a flat density, it's going to be linear. Okay. Any questions about this over here? Yeah.
What exactly is the support?
The support is the range of x values. This is the range of the domain for which the probability is non-zero, right? So in this case, the homework example was 0 to 1. So everywhere else on the real line, it's 0. So it's called the support. Okay, any questions about this here? So we can now use this to do the next homework problem, which was what is the CDF of this function? So the CDF of 3x squared is going to be integral 0 to x 3y squared dy, and this is going to be nothing more than 3y cubed by 3 0 to x, which turns out to be x cubed. Okay, so the CDF is x cubed. Okay. Any questions about this? Okay, and we'll write this as f of x equals x cubed. Okay, so having done this, we can now use this to do something actually useful. So I call it a stupid trick, but actually it's something that if you never remember anything else from this class, many years from now, this is one thing that you're probably likely to use. Okay, the one thing you're going to use is how to generate values from a distribution where the distribution is arbitrary. So let me give you an example of this. Let us say that you're writing a simulation, and for the simulation you need to generate the, so I'll give you a specific example. So one of my students was trying to study data center traffic, and somebody had gone and measured data center traffic, and they had found that the probability that a particular number of bytes is transferred from one computer to another computer in the data center follows some density function. Okay, so we could say on the x-axis, okay, we have the number of bytes transferred. So of course it's discrete because number of bytes is discrete, but because there's so many discrete values, you can just assume it's continuous for the sake of just to make it simpler. And so we have this density function that represents the number of bytes transferred, probability a certain number of bytes transferred from computer to computer. So let's look at it like this. So here is my, so basically there's some probability I have, so I have some density function. Okay, it looks something like, okay, actually it looks pretty much like this. Okay, so this is the maximum number of bytes transferred, and this is 0. And this is the density function f of x. Okay. Okay, fine. Now what you want to do is write a simulator so that when you are going to simulate a certain number of bytes transferred, you're going to generate random variables, random values, which are going to be from this distribution. Unfortunately, all you have is the printed paper. Okay. And it's a PDF file, and you write to the authors and say, can you tell me how you simulated your system, what you measured? They refuse to give you the values. Okay. But you need to run the simulation anyway. So what do? What you do is you use this trick, which I'm going to tell you about in just a moment, and it's going to work. Okay. So what you do is you take this over here, and this is the, as I said, it's a density function. You compute the cumulative function for this f of x like this. So it's going to be monotone, and it's going to go up from here to here, and it's going to be 1 over here. Okay, so that's the cumulative function over there. You can see it's going to look more or less like that. Yeah. Beg your pardon? Oh, I'm sorry. Well, the thing is, at 0, the density is over here. It should be, wait a minute. Yeah, it's supposed to start at f of 0. So it's going to go pretty fast up. Let me see. It's going to be 0, of course, yes. Okay, let's just draw it like that. I wanted to join somewhere up there. It will start at 0, sorry, because 0, it's always going to be 0 and 1, because the cumulative density starting at 0 is 0, but if there's a lot of mass close to 0, you'll find it kind of shoots up pretty fast. Okay, but you're right, it doesn't start in the middle. That's a mistake. Anyway, we have this function over here. What we want to do is we want to generate the values from this density function fx. So first we do this, and the second thing we do is that we're going to generate uniformly distributed values, okay, uniform in the range 0, 1. Okay, and so what you're basically doing is that you're going to be generating values that are uniformly distributed along this one over here. And when you generate a uniform value over here, let's say you pick this one, that tells you some value of f, and then you look back down over here, and that tells you some value of fx over here. So let's say this one is x1, this is f of x1. Okay, so what you're really going to do is you're essentially generating values uniformly in the range of capital F and take the inverse transform. Okay, so you're computing essentially f inverse of u, where u is uniform in the range 0, 1. Okay, and if you do this, what will happen is that these values xi are going to be generated from the density function small f of x. Okay, to see this, what you have to do is to understand that the capital F of x basically is telling you over here. So let's say you have a certain amount of mass over here, so density in this range right here. Maybe I should choose this range right here. Okay. The density function, so let me get this exactly straight. So let's ignore the, actually what I'm going to do is I have to draw it larger because otherwise it's not going to be visible. So let's take this. Okay, so let's just zoom in over here. So this is capital F. Let's ignore small f for now. And it's always going to be between 0 and 1, and we have something that goes like this. Sorry, this is not 1. This is some value m. This is 1. This is 0. Okay, like this. And let's say I choose some x over here, and this one is x plus delta. Okay. Then the amount of mass in this range from here to here, okay, is going to be is integral x to x plus delta fx dx, okay, and that is basically equal to f of x, okay, approximately equal to that. So what we then have is that this over here, okay, is, so intuitively what's happening is that the more the density function, the higher the density in small f is, the more the rise in the capital, okay, capital Fx in the cumulative. And so when you project it over here, it spans a larger range of the 0 to 1, okay. And so it's higher probability that we're going to choose something over here, which means a higher probability of getting something in this range, okay, which is basically what we want, right? So let me, so because and I guess the other way of, so mathematically speaking, what we can do is we can say that for small delta, okay, f, capital F of x plus delta is going to be f of x plus fx, small f of x delta, okay. So what does this mean? So we have over here, this is going to be capital of f of x plus delta, and this one is capital F of x. So this gap between the two, okay, is going to be basically small fx delta for small values of delta, right? So if we have a lot of density in the density function small f, these two values are going to be further apart. And if they're going to be further apart, there's going to be more likely a chance that we're going to select that when we choose uniformly randomly in this range. Okay, so the sort of the procedure is then very simple. We choose a random value uniformly in the range 0, 1, and then what we do is we find the inverse of the cumulative, so f inverse of the u, and that's going to give me the value x, and this x that's chosen over here is going to follow the density function. So you just basically take the printed PDF, compute the cumulative, and then you can numerically enter that. You can sample it, numerically put it in your computer, and then you can generate uniform values and get this. Yes, Navid? Why is the formula wrong?
Delta is very small.
Yeah.
So f of x, that integral is very small. But f of x, if we have a large x.
F of x is between 0 and 1. It's never going to be larger than 1 by definition, right? F of x is between 0 and 1.
That doesn't make sense.
Okay. Why doesn't it make sense?
Actually, just consider that formula.
This one here, okay.
I think it's better to write f of x plus delta minus f of x.
Yeah. It's basically what I wrote over here. I just rewrote this in terms of okay, you want to write this like this. So f of x plus delta minus f of x over delta is going to be f of x, right? By definition. So if you limit, beg your pardon? Yeah, it's integral. So by definition, but that's by definition, right? I'm just taking the definition of the cumulative, and I'm writing it in this form. So why doesn't it make sense? So you said it wasn't making sense though. Here. This is the same thing, and this is basically for small delta, it's fx. Oh, I see. This one over here. Sorry, this is equal. So
It should be f of x plus delta minus f of x.
okay, you know what? If this is confusing you, forget this. Yeah. So this is what you should be looking at. Okay, because I was just making that up as on the fly. Okay, so just ignore me. This is correct. That one was trying to give you an intuitive understanding, which is confusing you, so forget it. Okay, it's not important. This is important for the discrete case. In the continuous case, I wrote down the formula for capital F. F of x is specifically given as f of x is going to be integral minus infinity to x small f of y dy. So that's the right formula. Okay, and then by definition, basically this is where we get from here. This is correct by definition, and then that gives you that. And then if that gives you that, then this is the same thing, right? Fx plus fx delta is fx to delta. For delta very small, limit delta goes to 0. And intuitively what happens is that the larger the density function, the more it expands, because delta is constant, right? So it expands over here. When that expands over here, a higher probability of choosing that. Okay? So that's how we get this. So and we can do the same thing for discrete. I'm not going to go into that. But for the discrete case, actually it's a simpler analysis, and there's a little figure which is similar kind of figure. But it's kind of nice, okay, that we can take essentially any density function, or even better, if they give you cumulative, it's even easier, and we can generate values from that range. And this is something we're going to do all the time. For simulation, you have to constantly generate values from a distribution, and this is how we do it. Okay. So I'm going to let you do the discrete distribution, the same trick for discrete distributions generating random variables. It turns out to be roughly the same thing. Instead, I'm going to go on to an expectation. So this is kind of one of the most important things about a random variable. Okay. So suppose somebody gives you some random variable and says, okay, here's a random variable. If you know nothing about it, okay, if you know nothing about it, I should say, other than its distribution, we can use its expected value as sort of a standard, as a sort of a stand-in for what the value, for what the random variable might be, right? So let's take that same example we started with. So I have the values 2, 7, and 9. For some discrete random variable, it was 0.2, what was it, 0.7, 0.1. So I give you this x is equal to this with some, this is the domain D, and this actually is the density function. So we will write that as f of x, and this is xd. So these are actually probabilities, not a density function, it's a mass function. So we have the probability masses. So somebody comes and says, here's a random variable xd defined in this way. What do you expect it to be? What do you know? And in many cases, we really care about the expectation because this is sort of the mean value, okay, of something. So mean value, or the average, or the expectation, they all have this connotation that intuitively, if you didn't know anything more, this is what you'd have. This is what you'd expect it to have. This value you'd expect it to have. So if somebody tells you the mean Q length at the Tim Hortons and Davis Center is 5, okay, then if you knew nothing else and you went and looked at it, you'd expect about 5 people. On the other hand, if the mean value was 50, that means that, on average, there are 50 people over there. So we have sort of this intuitive notion of on average, what are things like. That's why we talk about average temperature of, during the week, average temperature in a month. Okay, that's okay. Yes, and then use on average, learning nothing. The break is over. Okay, thank you. Okay, so what we define as the expected value of xd is going to be just the product. Basically, it's going to be probability of x equals xi times the value xi itself, recalling that xi is a real, right? So we can actually do this multiplication. So in this case, we would just multiply this out like so, okay? And so this is 2 times 0.2 is 0.4, 7 times 0.7 is 4.9, and this is 0.9, and we sum it up, okay? So there's a summation that's missing over here. And it's going to be 4.9, so 5.8, so 6.1. So we say the expected value is 6.1. Okay, so this is kind of fishy. Okay, why? Okay. What's wrong with this? Or
It's not in the domain.
it's not in the domain, exactly. So you're computing the expected values. So somebody says the values are 2, 7, or 9 with some probabilities, and you say, oh, the expected value is 6.1, and it says, well, that can't be a value that you could actually have. So with discrete random variables, the expected value is doesn't mean too much. Okay, we can say, well, 6.1 is sort of close to 7, so probably this is likely, okay, which is true. 7 has a value 0.7, but basically for discrete random variables, the expectation is can be a value that's actually not even in the domain, okay, and so you have to be somewhat careful about what it means. Okay, for a continuous random variable x of c, the expectation, which is written like this or E, capital E, is going to be integral minus infinity to infinity x f of x dx. And the understanding, the implicit value, the implicit intuition here is that the value x has the density of fx roughly, okay, or you can think of it as hand wavy, the probability of x, but actually what we mean is that in the small value from x to x plus dx, the contribution of that range x to x plus dx is x fx. Okay, so the value itself x, and then this is the amount of mass next to it. So if you were to look at this, This is our density function. Okay, and the area under this sums to 1. So if I take some value, let's say x1, and you look at some small thing. So this small rectangle over here is sort of the contribution of x1 to the total probability. So we can roughly use this integral to tell us the expected value. So to do the, so for the homework example, for example, we had over there the f of x was given as 3x squared. So the expected value of x is going to be integral minus infinity to infinity x times 3x squared dx, which is going to be 3x cubed dx, which is 3 upon 4 x to the 4, 0, 1, which is just 3 by 4. So the expected value of this is going to be 3 by 4. And if you remember, the density function kind of sloped up to the right. It was something like this. Okay. So values towards 1 are sort of more probable. So it's not surprising that the expected value is sort of towards the right end. It's not 0.5, it's not 0.2, it's closer to the right end, it's 3 by 4. Okay? So that's the expectation of this random variable over here. Okay, any questions about this? Okay, so that's the definition of expectation. I lost my place. Let's see over here. Okay. And if we don't know anything else, that's what we would choose. So there are some very important properties of expectations. So the reason why the expectations are useful is because, as I said, in many cases, all we know is the distribution of the random variable. By the way, knowing the distribution of a random variable is already quite difficult. Okay, it's already quite difficult because we are going to tell you all possible values and the probabilities of all possible values. In real life, we don't know the distributions of most random variables. Okay, we can only kind of sample it, and I'll talk about sampling in just a moment, but we're just sampling it and kind of guessing what the distribution is. So we often have trouble just telling what the distribution is. The expectation is kind of summing up everything we know about that. So even if you don't know the distribution, hopefully you at least know the expectation. So it's kind of summing up the whole distribution. So if I tell you a random value and you say, what is the distribution? You say, I don't know. It's, you know, it's complicated, but I'll tell you what the expectation is or the mean value is, and then that gives you some idea. Of course, many random variables which are completely different from each other could have the same expected value. Okay, so for example, if you have if we already saw in the case of a discrete random variable, the expected value was something that it couldn't even assume. For a continuous random variable, if you have a density function that looks like this, the expected value will be something like this in the middle, right? Because you'll have some mass from here, some mass from there. That's why it'll be in the middle. In fact, it's a value that's not even probable. Okay, and so any multimodal distribution, any distribution that has multiple modes or something like this, okay, we're going to get something which is actually not even particularly meaningful, though we end up using it anyway. Okay, so I'm going to state some results for expectations, which all basically just follow from the definition, but it's not, I'm not going to prove it. It's really easy to show though. So first one is for constant. If you have constants a and b, then expected value of ax plus b is going to be a expected value of x plus b. So in some sense, we can treat the expectation like a linear operator. We can take out the linear values out of it. Second, expectations sum up. So the expected value of x plus y, okay, is equal to the expected value of x plus the expected value of y. And this sort of generalizes to any number of random variables. If you have 10 or 100 or 1,000,000 random variables, the expectations just sum up like this. Okay. And the third thing is this notion of the function of a random variable, and we'll look at an example of that. So the expectation of a function g, of a of a discrete random variable xd is given as sum over I g of xi p xi. So what we're saying is that we are going to take the density function, instead of multiplying with xi, we're going to multiply the g of xi instead. Okay, that's the meaning of this. And I guess I'll do an example of that just to show you what's going on. So let's take that same random variable over here, 2, 7, and 9, and I want to compute the expected value of e to the power x. Okay, that looks really crazy. You know, what does it mean to the expected value of e to the power x? All it means is that it's going to be the first value 0.2 times e to the power 2 plus 0.7 times e to the power 7 plus 0.1 times e to the power 9. Okay, it's whatever it is. Okay, so that's what we mean by expected value of a function of a random variable. In the discrete case, it's going to be this. In the continuous case, we're going to say that the expected value of g of some function xc is a continuous random variable, is going to be integral minus infinity to infinity. Instead of having x, we're going to have g of x fx dx. Again, intuitively, with the expectation, we have x fx dx, and we're going to replace x by g of x. So if we take some continuous random variable, so in the homework, for example, we had f of x was equal to 3x square. So expected value of capital X square is going to be minus infinity to infinity. Okay, so we're going to do g of x. So g of x is the square. So it's going to be 9x square, sorry, 9x to the 4, okay, times, so g, where am I doing? Okay, gx fx dx. So gx is the square, okay, and then we're going to multiply that by, what am I doing over here? I'm sorry? X square, yeah, I'm sorry, yeah, x square times, okay, I really should look at my solution here instead of winging it, right, times the 3x square dx. So this is g of x fx dx, okay, and that's going to be integral minus infinity to infinity 3x to the 4 dx, which is going to be just 0, 1, so 3x to the 5 by 5, 0, 1 is going to be 3 over 5. Okay. So that's this. We just basically plug g of x, x square, and f of x from before, and we get exactly that. Okay. So the answer is 3 over 5. Okay. So the thing is that this notation is kind of somewhat confusing, and so yeah.
I think the boundary of the integration should be from 0 to 1.
Beg your pardon? Yeah, because it's supported 0 to 1, so this becomes 0 to 1. So you can just call it 0 to 1. Okay, it's the same thing. It doesn't matter. Okay, because it's only defined in the range 0 to 1 in the definition of the variable x. Right? So integral is the same. Okay. Any other questions? Okay. So the important point is that whatever function we have x square, that basically goes there. Okay. That's all we have to do. So if it's expected value of e to the x, for example, and I keep saying e to the x because that's how we do moment generating functions, the expected value of e to the capital X over here would be, instead of x squared 3, so it would be e to the x, 3x squared dx. Okay, and then we could evaluate that as we wished, and whatever it is would be called the, in fact, the moment generating function of, if this was e to the x, expected value of e to the x, then that's what we get over there. Okay, that would be the moment generating function of the variable 3x squared. Okay, so these are the 4 definitions for expectation that are important. And right. And so one common mistake that students make is to think that, so I should probably say, expected value of g of xc is not equal to g of expected value of xc. So we can't take the g out. You can take constants out, right? We can take constant multiples out, but we can't do it this way. Okay, so that's a mistake. You can't do that. Okay, let's now look at the variance of a random variable. So the variance of a random variable is just a special function of the random variable, which is x squared actually. So I should be, well, variance of x is actually, or I should say, I should take it back, it's a special function, expected value of x minus expected value of x. Okay, where to put the square? Square. Okay, so it's an expectation on the difference between the actual value and its expected value. Okay, and so what we have is we have some. Let's just do a discrete probability mass function. So we have some probability mass function like this. Okay, and let's say they computed the expected value to be something like this. So the difference between the values that you have and the expected value is going to be the variance of this. So actually, I'm going to be so. Let me first show you how to expand this, and then I'll explain to you from sort of a statistical perspective what this means. So for now, we're going to assume that we exactly know what the expected value of x is. Okay, it's a number that's given to us, and we want to know what this, how to compute this. So this one we can compute as expected value, and you can just expand the square of x squared minus 2x expected value of x plus expected value of x squared. Sorry, yeah, x, oops. We're just expanding that over there, and this becomes expected value. Because it's a summation, we can break it up as 2 expected value of x expected value of x. Let me just write this down. Plus expected value of x. So am I doing this right? Yeah. Okay. And so how do we get this? Well, this is the expected value of minus 2 times x times expected value of x. So this expected value of x is some constant, right, as far as we're concerned. So we can pull that out, and we can pull 2 out. So this 2 expected value of x is just a constant that's been pulled out. And so what's left is expected value of x. Okay, so that's how we get 2 of this. And this just becomes expected value of x squared minus expected value of x whole squared. Okay, and this is a very useful identity, because what we're saying is that we can write the variance of x in terms of 2 expectations, one on the expected value of x squared, and the other one is the expected value of x, but we're just squaring it. So let me say just a word about what this means. Okay, when we have a random variable in real life, nobody is coming and giving you, here's the distribution, here's x, here's the distribution. Instead, you have to observe it, right? So if you want to tell you find the distribution of Q lengths of Tim Hortons, how do I do it? Right? I'm going to go there, I'm going to watch it, right? I'm going to watch it, say right now it's 5, goes to 7, goes to 3, whatever. And I'm going to basically say, come up with a series of numbers, okay, which are the observations of the random variable over some period of time. This constitutes what's called a sample, okay? So it's a sample of the of the random variable. And now we have a problem, which is that how do we know the sample is accurate or representative? Okay, does it really make sense to use this as a sample? So let's say I sample between 2 a.m. and 3 a.m. in the morning, every morning, the Q length. Okay, and I said this is the sample. This is what I chose. Well, it's closed at that time, so it's 0. So you say, yeah, the expected length, Q length of the Q at Q importance is 0. I'm done. Okay, that's kind of stupid, right? So you say, no, I'm going to sample between 9 a.m. and 10 a.m. on Sundays. Okay, that doesn't work either. So you say, no, I'm going to do 9 a.m. to 10 a.m. on weekdays. But then you say, well, is that representative of the night? No. So what is representative? And the short answer is, we don't know. Okay, it's whatever you can convince your readers as being representative. Okay, okay, we don't know. There's no good answer to what's representative. To come back to this, what we have over here is that we're going to sample this, and let's say it's representative. You agree and I agree, and the reviewers of your paper agree it's representative for some reason, whatever it is, you convince them. What are you going to do? You're going to compute the sample mean, okay, which is just the sum of the values, okay, sigma xi by n, where n is the number of values, and say, okay, this to me is the expected value of the random variable. That's what you're going to say. Okay. Now the problem is that you actually don't know if it's true or not, and so what we have to do is we have to sort of guess the degree to which we are accurate. Okay. And the whole problem in statistics and hypothesis testing is the degree to which we're actually working. This approach is working. So all I want to say here is that in the same way as you're going to compute the expectation of x, the mean, we also want to compute its standard deviation. And one hint of how to do it is, again, this is a sort of practical tip, is that we compute two running counters. One is the sums of squares, and one is the sum of the values. So if I have a loop, okay, over the trace file of the log, I'm going to keep a running sum of squares, running sum of x, and then the value n itself. And then if I divide the running sum by n, I'll get the an approximation of the expected value. And if I take this divided by n, that's an approximation of the expected value of the square. And then if I take this difference, then I will get essentially the estimate of the variance. So in practical terms, just two variables and a loop will get you the variance. And if you take the square root of that, that's the approximation of the standard deviation. Okay, so that's basically all I wanted to say about variance. We won't study variance much in information theory, so I just kind of tossed that in. Next time, I'm going to actually cover only a few things. I'm going to cover Gaussian variables, and then I'm going to cover just joint and Bayesian networks. So 1.5.2 and I think 1.7, whatever the joint distribution part is.